Okay, I have been banished to the kitchen, so hopefully there will be fewer interruptions. You can hear the soft sound of the coffee brewing in the background. That's right, we drink coffee at night. So, let's review. Remember that this equation, along with our new gas law of 8.314, our new gas constant R, that stuff's in the purple sheet. So just it's not surprisingly, it's in the thermodynamics area, and then electrochemistry, which is coming up at the end of this unit, and then you will have used every equation on both pages of the formulas. So we'll be ready to roll. But this does relate delta G to KEQ. There is kind of a little trick, and this will help you get ready for some of those multiple choice questions where you just have to kind of make estimates and not actually plug the numbers in your calculator. Like this right here, they said if you just know that RT basically equals 8 times 300 or 2400 joules per mole. So that's an estimate, of course. From your purple sheet, it says right there it's supposed to be 8.314, and the temperature is supposed to be 298. So you just round them and you say about 2400. So therefore, since G is on the top right here, if G is greater than 2400, then K will be really small. In other words, almost all reactants and a non-thermodynamically favored, non-spontaneous process. All right. Now, if 2400, if it equals about the same, and delta G is approximately equal to 2400, then you're just about at equilibrium. And if it's less than, when you look at delta G, then you know that's going to be a negative number, and that would give you a large KEQ value. And that's just using the natural log inverse there. Okay? So, as it says on the bottom here, you can just use this to estimate. So what I want you to circle on this page is that RT is approximately equal to 24. Highlight that right there. That's a good one to know right here. Okay, so again, if delta G equals 0, you're at equilibrium, and the KEQ constant would be equal to 1, which is very rare, but in that situation, there's no more movement in the reaction. And if delta G is really big, meaning we'll use that 2400 or 2.4 kilojoules, then you'll get mostly reactants, and it'll be super non-spontaneous and really small, meaning negative, of especially less than a value of 2400 joules or 2.4 kilojoules, then you're going to get mostly product, in which case that's a very larger KEQ value. So this is kind of a nice summary table to talk about those things. So you look at this reaction right here, and so this would be like a multiple choice question. Actually, A through D is like a multiple choice question. Good one, Chalmers. So you got delta H being negative 20 kilojoules, and delta S being negative 400. Okay? Now, both of these things tell me that this is not a favored reaction thermodynamically. Okay? The delta H has a slight value, but if you look at that delta S value, that is really, really small, and systems will favor the more disorder. So when you look at this delta H minus T delta S, and you throw in 20,000 joules, because you remember you're doing that, being negative, and then this value right here being close to 300, you can look at these two numbers and you can go, hey, you know, that's going to end up being on the positive end of about order of 100,000 joules once you crunch those numbers. Okay, so that would tell you that you have very few reactants in the problem. Okay, so this delta H just simply wasn't a big enough negative number to keep this negative, especially when you threw in, this is a pretty small delta G value. Because remember, most of the time they're in kilojoules, and quite a bit higher than that. And our cutoff point was 2,400, or so it's got to be quite a bit larger. So anyway, the system contains mostly reactants because it is just non-thermodynamically favored. Okay, so that's what we're looking at. So this multiple choice question, the answer is C. All right, going to heavily favor the reactants. All right, so those are the kind of applications that you have right here. Now, something like this, the delta H is negative 198 kilojoules per mole, and the delta H is minus 188. What is the value of Kp at 298 degrees Celsius? Okay, so notice it's not a multiple choice question. They're actually asking you to find this out. So you're going to plug in those values, and you're going to write this delta H as a joule amount, because we're going to need that eventually. And since delta S values are already in joules, it's an easier, quicker fix to just turn this one. But this we're going to use sig figs. We're going to punch it in the calculator. This would be a free response type of question. So you got a delta G of minus 142. But that's not really what they're asking. They want to know what the case of P is. And since these are all gases of the partial pressure, so what you can do is use the same formula. And again, this version that's written right there is not on the purple sheet, but you can use the version of the delta G equals minus RT ln Kp, and then just rearrange it, or you can just plain old memorize this one that we can use there. So we've got the delta G figured out, and you want to be careful here because it's a negative of a negative, and you got to do the parenthesis thing, and just be real careful with the order of operations, because you're going to take e to this whole power. So I would really be careful about crunching that number. And so this is obviously a really big equilibrium constant, meaning you got lots of products. So they say far to the right, way off there to the right, which is what we would expect, having such a large negative value for the delta H, which tends to really favor these reactions. So essentially what happens is that factor of the the delta S becomes less significant when that delta, when this delta H is so large, then that delta S, it doesn't change it very much, as you can see. Okay, because it's just such a big number, and that is what would be expected. Okay, now for the above reaction, Kp equals 36.5 at 400.0 K. Find delta G. So here's how we're going to solve this. Delta G equals negative RT times the natural log of Kp. And all you have to do at this point is plug in and solve, remembering to keep the negative symbol, and you might want to do the natural log first and then multiply it by those two numbers. That's how I do it anyway. Delta G equals negative 1.2 times 10 to the fourth. And remember, this answer will be in joules, and if they ask for it in kilojoules, you just got to remember to change that. It's a negative 12 kilojoules. So you say, well, slightly favored forward reaction, but not very much. Okay, and you remember this famous reaction that prevented the world from starvation. Interesting history, but it just doesn't want to go forwards. So that's the Haber process, and he's the one that discovered ways to make that go forward, even though it was not a very spontaneous reaction. Okay, this also is a little bit of review, and if you can look at, we used an analogy of a pencil. I got one right here, and a lot of people think when you break a bond, it gives off energy, and that is simply not the case. You have to break a bond. So you got to put energy into it to do that. Okay. Now you have a new thing but you had to invest energy in order to do that. So this statement is worth highlighting again. Okay. And that's what we're going to do right there. Okay. So make sure that you get that highlight. Is that the past tense of highlighted? All right. This, remember, we had the same exact slide, that the potential energy, think of this as, books stacked on a shelf. Just turn this sideways. And this has a lot more potential energy when they're farther apart. Okay? So the potential energy decreases as they get closer together, just like it would decrease if you put it on lower shelves on a book. So that's how we relate that energy concept to that. Okay? Now, the last thing we're going to talk about, we have to kind of break up piece by piece. It gets a little bit complex here. It's called the enthalpy of dissolution. Where you're breaking ionic bonds, all right? And then hydrogen bonds between some of the water molecules also must be broken, so that they can surround the particle, okay? So they get all up in their business there, okay? And they get surrounding them all over the place. Now, both are endothermic processes. So go ahead and highlight that, and that these hydrogen bonds must be broken. Okay? So, you got to invest energy to do both of those. But an ion dipole force of attraction is established. That's a new type of bond. It's not covalent or ionic, but it is an ion dipole force, which is significant